zone refining CCC, here the pKa may be more important. Here, this peak will be eluted earlier, so it switched, but we can see the both factor will affect this separation. So we know sometimes only the partition coefficient is not enough to separate the compound, especially for this catecholamine compound. This compound is very polar. In most solvent system, it will be mostly partitioned into the aqueous phase. So in this case, we add a affinity ligand into the stationary phase. So we can see the first chromatogram, if no affinity ligand, all this peak eluted in the one peak. After you add this affinity ligand, all this catecholamine can be completely separated. So we also can apply this affinity ligand in pH zone refining CCC. In this case, the pH zone refining CCC, the separation factor will be determined by 3 factors. First is the hydrophobicity. One is pKa, then is the affinity to the special ligand. This is the separation of this catecholamine by pH zone refining CCC and the affinity ligand. We can see all this peak was clearly separated with this all pH zone. CCC method to separate the free peptide is also challenging because most of the peptide also is they have a very similar polarity, so it's very hard to select the solvent system to separate all different kind of peptide mixture. So in here, we add the affinity ligand in the stationary phase. Use the pH zone refining CCC to separate the free peptide. We can see this is a group of hydrophilic peptide. This can be clearly separated for this. This is only the model for simple peptide. This is a hydrophobic peptide. We can see all these 4 peptides can be clearly resolved. We use this method to separate some natural peptide too. It's very useful. We can get like a 10 grams quality, 10 grams sample added to the regular semi-preparative CCC column. It get very good result. I didn't bring the example for here, so. And this one is a chiral separation. We can add the chiral selector in the CCC stationary phase. This is the 4 pair of the chiral compound. After this is no chiral selector. After add the chiral selector, we can see this 4 pair of the chiral compound was clearly separated. This is we call the chiral CCC. So we also can apply the chiral selector for the pH zone refining separation. This slide showed we separate the DNB leucine. It's enantiomers for 2 grams of mixture of enantiomers for this compound. So we add the retainer acid and the chiral selector into a stationary phase, eluted with ammonia. We can see even these enantiomers can form this all pH zone with the help of the chiral selector. So this is this is analytical CCC to detect the purification of each PS. We can see this each plot is clearly separated. This is this one, this is this one, and this is the mixing room. So they go back to the CCC, the pH zone refining CCC separation of the natural product. This natural product, this is the lignin. So this compound is the weak acid because it has a phenyl group. In this case, if low the eluted base, if you only use ammonia, they cannot partition this compound to the aqueous phase. You have to use sodium hydroxide as a elute base. Sodium hydroxide can be make the phenyl compound ionized to go to the lower phase. This is where this compound was extracted from a plant from Africa. So Dr. Huang's group in Johns Hopkins, they found this compound have a very good anti-HIV activity. So we can see here, we can get two PS rooms. One room we got NDGA. This is all this group is hydroxy. Another zone is a mixture of the 3-methyl and the 4-methyl. This here, because maybe this pK is too close, hydrophobicity also is too close. We cannot completely separate these two, but these two compounds can be from the same plateau, can be the mixture eluted from here. So this is a larger scale separation of that same crude extract. This is our story for this compound, because a pharmaceutical company wanted to test the clinical trial for this, I think the 4-methyl NDGA. They need 10 grams of pure compound. So that time, Dr. Ju from Pharmatech Technology, he got this contract. They gave him like kilograms of crude extract. They want him to get the 10 grams of pure 4-methyl NDGA during the 1 month. Because he saw we had been separated this compound use the pH zone refining CCC. So he think that job should be easy done. He charged the company the small amount of money. Then after I talked with him, he really realized how hard this project could be, because this kilogram quantity of crude extract, you get 10 grams of pure natural product during 1 month. But finally, he used his largest scale CCC developed in his lab. It's 800 milliliter per the capacity. So that time, I don't know that Dr. Sutherland have that big instrument. So finally, we found that 800 instrument use the pH zone refining CCC. They can handle the 20 gram to 50 grams crude extractions. So after separation, we can see this have two clearly plateaus. One is NDGA, one is 3,4-methyl NDGA. This is a mixture. We have to collect these fractions and then separated these two by normal CCC. This is a good example for combine the pH zone defining CCC and the normal preparative CCC. So after purified these 3,4 methyl compounds, we found we got a lot of side product of NDGA. This is all the hydroxy. The only difference is one methyl difference. So we decided to put this NDGA, methylize this NDGA, use a chemical reaction. This is a product after the chemical methylization for the NDGA, we separated this reaction mixture. We also got these 4 pH plateaus. One is unreacted NDGA, that's a small amount. Mostly is a mixture of 3 or 4 methyl NDGA. We also have a little bit overreacted dimethyl NDGA compound. So this provides another way to get the 4-methyl NDGA. So this is a larger scale separation compared with the previous slide. Okay, this is another application of the pH zone refining CCC for alkaloids. This work was did in Dr. Yang in Beijing New Technology Institute. He also put a different size of the crude extraction, did the pH zone refining CCC. He found after increase the sample size, he got another plateau. The major compound in his extraction, I think he already, his crude extract already processed after some kind of processing. It's not directly crude extraction, but it's also in mixture with something. So he got the major product is the first compound, this compound. So after increase the sample size, he got another zone, pure the zone for the second compound. Also, he collected the mixing boulder. He separated another 2. So in this case, the pH zone refining CCC, in large scale, he can get 2 pure alkaloids. From the mixing zone, he got the actual compound. So actually, for the natural product studies, this mixing zone is also very important because the pH zone refining CCC can concentrate the small amount compound during this pH zone. So if you want to find some real compound, maybe the new structures or some new activities, this mixing zone may be very important for the research studies. So this is another example for the alkaloid from natural product. So this is we can see this 2-compound structure is very close. It can be clearly separated during the pH zone refining CCC. It has its own pH zone. This is the pure fraction. This is the pure fraction. So this is also recently publication from Wang's group. So I think okay, the difference structure difference here have a double bond here and that. So we can see these two also can be clearly separated by this pH zone refining method. Okay, this is a sample from the fungals. So this is Dr. Gay Harris' work in the Merck. So we can see this compound didn't have much UV absorbance. So the UV detector is very hard to detect them. But we can use PS room to detect this. This is after the separation, he analyzed this fraction by HPLC, then he got the figure of this one. But actually, this is not UV absorbance. So this is his HPLC fraction. He draws these peaks. We can see these three compounds is clearly separated, detected by this pH zone. This is these three compounds. You can see the structure is very close. This is a very good example for the use pH zone refining CCC in natural product separation. Okay, this is a list for the recently publication for the natural product. We list the samples, how much the sample scale, also the two-phase solvent system you can use for the different kind of compounds. They have alkaloid, peptide, polyphenols, carbohydroxide acid, and other compounds too. We can see they have a lot of examples, solvent system to be choose. Here, the most solvent system choose to use MBE. I think we can use all the other solvent system too. Why they all use MBE? Because maybe the early publication of the pH zone refining CCC use the MBE. But I think this method can use all the solvent system. The key of this system, when you select the solvent system, you will be tested in the acidic condition. If your compound is alkaloid, so if you test it in the acidic condition, most compounds should go to the lower phase. In the basic condition, most compounds go to the upper phase. If that works, then I think pH zone refining CCC, that solvent system should be works too. So this is a list of the retainer base and the retainer acid. Actually, the key of this one is we want this retainer base or retainer acid most partitioned in your organic stationary phase. So it's why we use triisoamine and TFA. You can use other too. But the key of this separation is your retainer acid must be stronger acid than the acetic compound you want to separate it. If you use a basic compound, this retainer base should be stronger than your samples. That means that the pK should be bigger than your sample. So this is a eluted acid or eluted base. This depends on your compound. If they can ionize in your case, for example, for the normal carbohydroxide compound, you can use ammonia to be ionized in the lower phase. But for the phenol compound, you have to use a stronger base like a sodium hydroxide. So we go to the conclusion. First, pH zone refining CCC can make the sample loading capacity increase over 10 times. We already see a lot of examples for this method. This is a great advantage for this method because we can use the regular CCC column to do the large-scale preparative separation. So the fractions are highly concentrated. This is very easy to understand. We can see all the diluted peak became saturated. We diluted as a rectangular peak. Also, this concentration is determined by the elution base concentration of the elution base and the elution acid. So elute acid. So I think the highest concentration can be go if it's not saturated from your solvent system. Sometimes if you put too concentrated, the salt will be precipitate. That is not good for your separation. So you can adjust this. Also depend on your sample size. If your sample size is relatively smaller, I recommend use a little bit low concentration. You can get the border, the fraction, the pH zone is a little bit longer. You can get a more clearly separated fraction during the middle of the zone. So if your sample size is large, so you better use a little bit high concentration elute base, so elute acid or elute base. So it depends on your fraction. It depends on your sample size. So yield is improved by increase the sample size. This can be understood by use the example I first gave, because the mixing room for the different size of different scale separation is almost kept same. So after you increase in sample size, your pure room is getting broader, so you get more pure compound. So this minor impurity are concentrated and detected and peak border. So this is, I already said this is very important for the natural product research. So elution peak can be monitored with a pH flow meter without the chromatograph. So that is another advantage. Okay, thank you for your attention.